Deep inside a 4,500-year-old structure, an exploration rover hits a dead end. Faced with a solid stone slab, researchers drill a small hole, feed a lens through the dust, and capture footage of a sealed space. The target of this expedition is the Great Pyramid of Giza. It is a monument that has dominated the Egyptian horizon for millennia. Constructing this massive tomb required extracting and assembling 2.3 million individual blocks of stone. Many of these quarried pieces are immense, weighing up to 50 tons apiece. This animated diagram visualizes the total mass of the structure. Stacking up 12 towering modern skyscrapers barely equals the 6 million-ton weight of the ancient Egyptian monument. Distributing that kind of extreme weight requires an enormous foundation. The base of the pyramid spreads across 13 acres of desert, easily encompassing the area of 9 entire football fields. Achieving this scale required solving a series of severe mathematical and physical problems. The builders executed one of the largest mass construction projects in human history entirely by hand, without a single piece of modern machinery. Before laying a single stone, surveyors had to square the 13-acre foundation precisely to the cardinal directions. They achieved perfect true north, south, east, and west alignments without using a magnetic compass. This diagram illustrates their astronomical solution. By tracking polar stars, the fixed points of light aligning with the Earth's axis of rotation, surveyors could map exact coordinates straight down onto the desert floor. With the grid locked in, they faced a second critical hurdle. If the foundation dipped even slightly, the uneven distribution of millions of tons of stone would cause the entire structure to collapse in on itself. To find a perfect level across acres of sand, engineers dug a perimeter of shallow trenches. By flooding them with water, they utilized the natural horizon of the liquid as an absolute baseline, chiseling away any bedrock that broke the surface. For precise measurements, they built wooden A-frames equipped with a plumb bob. As the tool rested on the stone, gravity pulled the string down. Builders knew the surface was perfectly flat when the thread rested exactly over the center line. Lacking microchips or digital sensors, the architects leveraged the reliable, absolute laws of geometry, the downward pull of gravity, and fluid dynamics for the foundation. Securing the raw material presented a new bottleneck. The standard tools of the era were made of raw copper, which is far too soft to cut through dense limestone blocks. The solution was an early chemical breakthrough. By alloying copper with arsenic, blacksmiths forged hardened chisels. Workers drove these tools into the bedrock with wooden mallets, carving out massive, uniform blocks through hundreds of hours of manual striking. The highest-grade limestone required for the outer casing wasn't even located in Giza. It was quarried in Tora, 250 kilometers away from the construction site. Navigating that distance required a synchronized naval operation. Heavy wooden barges loaded with massive stones floated slowly down the river toward the plateau. The bottleneck narrowed further at the docks. Hauling a single 50-ton block onto the dragways demanded the physical exertion of up to 500 men, pulling simultaneously on heavy ropes. The defining characteristic of this project was extreme organization. They scaled raw human muscle into a synchronized industrial machine, coordinating millions of manual tasks over decades without breaking the supply chain. Once the material arrived, engineers had to push 50,000-kilogram loads against the relentless pull of gravity, eventually reaching a peak altitude of 480 feet. This 3D wireframe illustrates the prevailing architectural theories for vertical transport. Massive external ramps, built in continuous zigzags or tightly coiled spiral pathways, allowed labor teams to slowly drag sleds up the ever-steepening incline. The physical challenges intensified deep inside the core. The internal load-bearing chambers, meant to protect the pharaoh forever, were constructed entirely from massive blocks of solid granite. Granite is one of the densest, most unforgiving materials in the Earth's crust. Modern fabricators rely on diamond-tipped grinders to slice through blocks like this, precision-cut coffer resting heavily inside the king's chamber. The ancient masons bypassed the lack of mechanized diamond blades with heavy, toothless copper saws. Workers poured a slurry of sand and gravel under the metal edge, relying on the extreme friction of abrasives to eat through the rock. This heavy friction grinding method was agonizingly slow. Slicing through just a single slab of granite consumed up to 4 straight months of grueling labor in total darkness. Faced with a hard physical limit to their material technology, they overcame the obstacle by sacrificing thousands of grueling hours to force the hardest stone on Earth into perfect geometry. In the 4.5 millennia since those ramps were dismantled, the plateau has absorbed the violent shocks of dozens of severe earthquakes and massive desert storms. Through it all, the intense, calculated weight distribution of the masonry held. The structure effectively resisted thousands of years of kinetic force, remaining entirely unmoving against the skyline. Which brings us back to the robotic rover, creeping past the newly drilled hole in that solid stone slab. Its light sweeps over a tunnel completely hidden from humanity since the last block was sealed. We now understand the mechanics of how this mountain was engineered, but the mysteries locked inside its deepest protected chambers are just coming into light.